this first math reading group of the year, and we're starting with more differential geometry, specifically curvature and tension. For the main reason for that is that I was not able to find a good explanation for it last year, and I got a bit angry or upset about it. So uh, now I'm fixing that. So as I was saying before, we noticed the technical problems. Um, the good news is that I do have some interesting explanations for it. The bad news is that it's still a bit abstract, at least in the as far as the differential geometry sense goes. It's still like the definitions of curvature and tension, not tension, torsion, are very abstract. And so, like really, unless you work through some examples and some like calculation with it, it's hard to make any sense of it. But we'll see what we can do. So yeah, brief outline. So I actually break this down into three parts. First, I'll give an example of curvature and torsion, but for curves in Euclidean space. It's a specific special case, but it's nice because it gives a lot of the flavor of the more general sense. And then we'll jump onto that. So the more general definition of curvature, namely the Riemann curvature. Also note that there's multiple different curvature and curvature tensors, which does not help. Um, and then I'll bring back, so it's sort of if you look at the structure of this session, it's going to be easy, a bit harder and abstract, and then a bit easy again. So hopefully you'll still be breathing at the end. So, and essentially we're finishing with curvature but for surfaces. So because it's been a while and it's always good to have a refresher on differential geometry, we're always working with something called a manifold, which is, you can think of it as a collection of points that forms a smooth surface, and smooth means that if you go really close to a point, it looks like a plane, at least it looks flat. And so, in fact, you can like imagine take a point and look at like a plane that's tangent to that point, and that's called a tangent space, and it is in fact a vector space specifically in differential geometry. It's a vector space of infinitesimal displacements around that point, and you can also think of them as tangent vectors to curves passing through that point. And so at each point we have a vector space Tp of m, so it's the tangent space at point P. And usually, although we won't be using that much today, we have something called an inner product on the tangent space defined by a metric, the Riemannian metric G. And the other big thing that we can have on a manifold, and in principle they can be completely separate, but there's a sort of a nice natural way to have one that works with both the metric and the second thing called the connection. So the connection is a bit hard to explain, but the idea was that we wanted to be able to translate vectors from the tangent space at one point to the tangent space at another point, and do like compare them and do operations with them. We wanted to be able to like follow a curve or take a point, pick a direction, and like go to that direction and figure out how the other vectors should be transformed. And that's all done with something called a connection that allows you to do sort of like parallel transport, covariant derivatives, and all sorts of crazy stuff. And for example, it's described as something like this. So for example, if I have a vector u at p1 and I want to obtain u prime at p2, I do this operation and it gives me u minus this operation that takes, so dxi is like a displacement in the ith coordinate. And then I have this like weird object with multiple indices, although it is not a tensor, called the connection coefficients. And roughly this describes how like my basis vectors of my tangent space get transformed. And so today it's really more the connection that we're going to play with, but let's keep on. So now we're back to the like the really at least not too abstract stuff. So specifically, we're talking about curves in R3. So R3, it is a differential manifold. It is very simple because the metric is simply given by the identity matrix, and the connection is flat. So the all the connection coefficients are zero. So there's no headache to have here. But it's still interesting to consider this case. So let's say, imagine we have a curve, gamma, and we could define it as like an infinitely long curve, but let's suppose it has a domain AB. And so it's basically described by three functions for each coordinate. And we'll ask here that my functions are at least C1, so they're all differentiable, but for later we might need that to be stronger, so we might need it to be differentiable like twice or more than that anyway. And so a natural vector that we can ask is so-called the tangent vector, simply the derivative of my curve, so the xi relative to t, which is the parameter that lets me slide along my curve. And because we have a curve that's embedded into R3, which is a manifold, we can ask about the length of that curve. And it's simply, let's say I start at t0 and end at t1 and want the length of the curve segment between these 2 points. I simply integrate the norm of my tangent vector at that from between these 2 times, or these 2 points, let's say. So that's nice and good, but usually when we use curve, we want to have a normalized stuff. So for example, like I could have 2 different curves that go through, but like the set of points that these curves occupy are exactly the same, but they don't go at the same speed through it. And so, like you might imagine, let's say, oops, I don't want to do that. And actually, I think what I was about to do was maybe not super clear. So, but if you've seen like stuff like animations, like animation curves, you know that okay, you can follow a path, but you can maybe like start slowly, then accelerate, and then slow down again, or you can go at like a constant rate. And so for a single curve, there's multiple like speeds you could have and go through it. So specifically for here, we want to be able to have like a sort of nice reference curve. And so what we can do is take something called a length parameterized curve, sorry, because notice that the length here, if I pick some t0 and I look at the length of the curve for t1 greater than t0, this is going to be a strictly increasing function, and so it's going to be invertible. And so that means that for any desired length s, or s0, I can find a unique t such that going from t0 to t, that segment of curve has exactly length s. And so I can define like my new curve as essentially it's the same curve but parameterized by s. And so the nice thing about this new curve here is that it goes through exactly the same points, but the length of the curve for s is exactly s. And so it sort of like goes evenly at always the same rate of distance, always the same speed for that curve. And note that this parameterization is always unique, but it's very useful. So we'll see in a minute why that's useful, but another thing we can do if we have curve, we might want to be able to find like an orthonormal basis of vectors around each point of the curve that also has to do with the curve. So a first vector we might want to do is simply take the tangent vector and normalize it, and that gives it a norm. So it's essentially, notice if my curve is parameterized already by length, then that's simply dx over ds. So very easy. And then, okay, I want another vector. I need it to be orthogonal to the tangent vector. And it turns out that taking the derivative of my tangent vector with respect to s is going to give me that. So we call that the normal vector. And why exactly is it orthogonal? Well, we can see that because we've defined t as being norm, right? The norm of t, so essentially the this inner product here is equal to 1. So the derivative of that should be equal to 0. And so if you apply the Leibniz rule to the inner product, that gives you that like the two, but that doesn't matter, but the inner product t with dt over dA, so essentially the direction of our normal vector, that's equal to 0, so that works. So we have two orthogonal vectors, and then because we're in 3D space, we can take a cross product of both to get a third vector, and we call that the binormal vector. Okay, so notice here, right? So the tangent vector, you can think of it like as a first order approximation of the curve. It's like the first derivative, and the normal, it's the second derivative. So you might have an intuition that curvature usually has to do with like second order or second order derivative. That's going to be a consistent thread in here. Okay, so now we have a basis of vectors. What can we do with? Actually, I think like I have a nice visualization for this, but I'll keep it that after I explain like curvature and torsion. So essentially, if you play around with these, and especially if we look at, so notice that by definition, the derivative of the tangent vector with respect to the length is proportional to the normal vector. And so if we call whatever that vector is k of s, and it turns out that k of s is simply the norm of dt over ds, and we'll call that the curvature. So here we're saying that the curvature of a curve is the rate at which the tangent vector to that curve changes. And if you imagine that like the curvature of a road, right? If you have a very sharp turn, that's like your tangent vector is changing a lot more, so the road is more curved, has more curvature at that point. If you do a similar thing for the binomial vector, you find that actually it's also proportional to the normal vector, and we'll call that one the torsion. And then if you look at the derivative of the normal vector, then you get that it's equal to the torsion times b minus the curvature times t. So it's nice because we actually have a set of differential equations for these three vectors. But notice that these vectors might not always be defined. So for example, let's say my curve is a straight line. Then okay, the tangent vector is constant. And so if I apply the definition for the normal, that it's 0. And so I have always a problem. And really, my choice of basis is undetermined, right? I could have like something, two vectors spinning around, and so it's not always defined for all curves. And you can also have some more problems, but let's not get into those. So okay, to give one piece of intuition about the curvature or curvature and torsion, let's look at the Taylor approximation of the curve around some point, and we'll only look at the second order. So if we take the second order Taylor approximation, then okay, we have the point, and then essentially the tangent times ds, so the first order, so that's not a surprise, and then we have 1/2 times the second derivative times d squared, and we know that that is simply the curvature times the normal vector. So what this tells us also is that at second order, again, this curve gamma it's a planar curve. Like it lies in a plane spanned by these two vectors, the tangent vector, the normal vector, and we call that plane the osculating plane. And so if we look just in that plane, let's say I'm looking close enough, another thing I can do is look at a circle, and let's say I want to have a circle that's tangent to the curve at my point gamma of s0. and it's the like in some sense the best circle, the circle that approximates the curve best. And it turns out that that circle is simply given by this equation. It's the circle with center. So I take my point, I subtract, or maybe I add actually the normal vector divided by k, and then the radius of that circle is going to be 1 over k. So the radius of the circle that fits my curve best is 1 over the curvature. And one thing you can think about, let's go back to this idea of a curve, right? So sorry, a straight line. Intuitively, a straight line has no curvature, right? It's flat. So in some sense, the curvature is 0. And if you think of in this picture, right, this also the circle, it's infinitely large, so the radius is 1 over 0, so infinity. If you're playing loose with arithmetic here. So even though analytically there's some weird stuff going on, intuitively it seems to work. So that's for curvature, right? It sort of describes how much the curve bends on that plane. And what about torsion? Well, so we know that curvature describes how the curve bends in a single plane. Notice that, let's say my binomial vector never changes, so its derivative is 0. That means that the torsion is 0, right? The tangent the tangent and normal vector might still change, but the torsion has to be 0. If that's the case, then that means that we're always in the same oscillating plane. So the curve is also in that plane. It's a planar curve. And so that means that whenever the torsion is not 0, that means you're sort of bending outside of that plane. And so that's what torsion means. It's how much your curve bends out of the plane. So I did whip up some basic GeoGebra for this. So here I have a basic circle, right? And I have a point on it. So here I'm plotting the tangent vector in orange, the normal vector in blue, and the binomial vector in green. And okay, if I spin my point around the curve, I can see that indeed the tangent vector changes, the normal vector changes, and it's pointing at the center, right? Because it's a circle, so we know actually what the radius, the curvature is. It's constant, and binomial vector never changes. It's always going up. Now let's say I change this curve a bit and make it go, instead of staying on the same plane, it's a spiral. So notice that now, ooh, okay, that should work. So now I do, I'm not staying in a single plane. And so if I move my point around the curve, I can see that both my normal and binomial vector change as I move around the curve. So that's that's an illustration of what's going on here. That really we have a curve that sort of looks like a plane, at least close enough, but then it goes out of the plane. I also like to think of it as like, imagine a paper plane in your hand, right? You have a paper plane bending in the same plane, but it can also spin around. And so the spinning around that's torsion. Okay, so that's enough GeoGebra for now. Actually, for today too. So now we're getting into the maybe less fun part. So let's go back to manifolds. So let's suppose we have a manifold with a connection, and really it's all about the connection. We don't necessarily need to play with the metric for this. And at least for now, let's consider a 2D slice of manifold. So we might have like an n-dimensional manifold, but we're just taking a 2D slice of it. So just a surface going through that manifold. And so that's going to be essentially parameterized by two coordinates, sigma and tau, and they're going to give me points on that surface or subsurface, p of sigma and tau. And so along that surface, I can take two tangent vectors, so the derivative along sigma and derivative along tau. those are tangent vector fields on the to the surface P. And so here I'm going to give the definition of the torsion and curvature tensors first, and then try to give the intuition, because yeah, as far as I can see, that's usually how people explain them. So let's define this torsion operator here. It's going to be take two tangent vectors, and essentially it's going to be I'm taking the covariance derivative alongside in direction tau of the dp over d sigma, and then I swap. So it's the covariance along tau of dp over d sigma minus the covariant derivatives covariance ah, covariance derivative along sigma of the other vector. So I'm swapping them. So you can see this is sort of a common pattern in differential geometry. You're sort of like trying to swap operators or swap some arguments in an operator to see if it commutes or not. And so in this case, we're trying to see if taking the covariant derivative along one direction of one thing is the same as taking the covariant derivative of in another thing. And on the right here, the more general definition. Um, if you don't know what this last term here is called a commutator, it's simply x, y minus yx. And here, like x and y are supposed to be tangent vectors, and so they can compose. And so, like the commutator is a measure of how much two vector fields commute. And so, for example, if this is 0, then you know that the xy is equal to yx. So that's why it's called commutator, because it tells you whether two things commute. And also, then this thing is going to be commutative when you're done. So, but anyway, so keep that in mind that you have this thread of like swapping the order of arguments. So if we have a coordinate system, we can express this tensor. In fact, it is a tensor in some of so tkij. And it turns out that the coordinates are very simple. They're simply given by my uh, connection coefficients, so gamma kij minus gamma kji. So I'm just swapping to the two. And notice that even though like individually the connection coefficients are not tensors, this one is. And so yeah, more you're sort of measuring some notion of commutativity for the covariant derivative, but we'll see that more later. Okay, so that was for torsion. Let's look at curvature. So curvature is a bit more nasty to look at. So let's take a deep breath. So suppose I have a vector field along P, W. Note that W does not necessarily need to be tangent to my surface P, right? P is a surface in my manifold, and just have a vector field in it. It doesn't need to be tangent to it. And I'm going to define R, and so typically people note it like this. So R, U, and V, W, but you can also write this as R as something that takes three arguments like U, W, U, V, and W, but it's usually noted this way. And again, it's this idea of sort of swapping the order of arguments to see if they commute. So here we're taking the covariant derivative along tau of the covariant derivative along sigma of W, and then minus the opposite. So the sigma covariant derivative applied to the tau covariant derivative and so on. So again, there's a more generic definition involving the commutator, but don't worry about it. The important part is that we can also express that into a coordinate system. And it turns out to be this a bit more nasty expression because we have like partial derivatives of the metric connection coefficients and then in combinations of them. So a bit nasty, so let's not worry too much about it. I'll have an example just now. So, okay, how do we interpret this like weird stuff? So let's imagine I have a point P and I have a tangent vector V at that point P. And then I want to look at what happens if I like take a rectangle. So let's say I take my point P and I move by some displacement epsilon I to point Q, and I can like parallel transport V to that point to get VQ. And then I can move from Q to R by some displacement delta I. So here, notice these displacements are in coordinates. So this is would be like a rectangle in coordinates. And so first I like go epsilon I to point Q, and then add delta I to get to point R, and I get VQR if I go that route. I could also go the opposite. I could like first go in direction delta I, and then to get VS at point S, and then go direction delta epsilon I to get VSR. And the point is that curvature means that like you might expect that these should be the same, but they can not be the same. And if they're not, that's because you have curvature in your space. Because that means so curvature essentially means that like the process of parallel transport is path dependent. You do not get the same thing depending on the path you follow. And so we can look at that roughly if we take like the expression of these VQR and VSR and express them at second order. So essentially it's a lot of calculation, but we have, okay, the first terms, that's order 0. These are just order 1, and then we have this order 2 that appears here. Notice that essentially all these terms are going to cancel out if I like take the difference between these two, and this is going to be what's left. And so it turns out to be essentially vk times my Riemann curvature tensor time both of my displacements. And so in one thing you can imagine curvature as describing is how much like yeah how much or distorted your vectors are if you go through different paths. So that's what's how you could explain curvature. What about torsion? So torsion is a bit slightly bit trickier. Notice this here, I'm not following the example of the reading because I didn't find them the most insightful. So I grabbed the syllabus of my own geometry teacher, but never mind. So for torsion, um, here it's going to be a bit arbitrary. Let's consider the effect of this operator. So it's the commutator of the covariant two covariant derivatives. Yeah, we're playing a bit loose, but we can always do that. So that just boils onto this. So it's similar to what we had done before. And you can think of this as essentially measuring the distortion when you make a round trip. So we're still going along this rectangle, but instead of going like both taking two different paths to R, we're just taking P, then to Q, to R, to S, and then back to P. And we'll look at the difference between the vector V after being transported through this path and how it is originally was. And again, if there is curvature or torsion, we should see something. And so it turns out that if you do the calculation and yeah, I saved you some brain cells here by not running it all. Essentially, you can express it as the curvature times your basic coordinates minus the torsion times the covariant derivatives of your vector field. So xm here is the vector field. And so what that sort of tells you is that curvature is, okay, it measures the part of parallel transport that's proportional to xm on the loop. In some sense, it's what's due to the you can think of curvature as like the bending that you do because you're moving a curved surface, whereas torsion, it's proportional to the covariant derivative, so it's a bit in a sense torsion is like the extra curvature that's not due to the fact that you're on a curved space. It's one way to think about it, but maybe not not always correct. Okay, so the more difficult part is over. You can breathe again now. So let's finish with something maybe a bit closer to intuition. So here we're still studying manifolds, but only 2D manifolds embedded in R3, so surfaces in Euclidean space. And so these are actually very like useful in 3D computer graphics, right? Because whenever you have a model in computer graphics, it's essentially, at least people think of it as a manifold or a discretization of a manifold. And for example, one thing we can take is given any point, we can find a normal to that tangent space. And note that they could be two, technically you can choose two. Either I could take like one direction or take the opposite, that would still be a normal vector, but we just have to choose one that's consistent. And so let's suppose that for every point of my 2D surface here, I'm picking the normal vector to my tangent space at that point. So let's call that n of p. So we can actually think of this map n from my manifold S as a map from my manifold S to the unit sphere. So it's a map from a manifold to a manifold. And so whenever we do that, right, we have a map from a manifold to a manifold. Because it's differentiable, it means that we can look at something called a differential, simply differentiating from one to the other. That gives us a linear map between the tangent space, let's say at so Tp of S, to the tangent space at n at on S2. So we have a linear map between two tangent spaces, and turns out that there's a couple of neat tricks. First of all, because we're in R3, the tangent space it's two-dimensional. The normal is also yeah, it's all the vector orthogonal to this normal vector, and it turns out that the tangent space in S2, well, it's actually the same tangent space. At least it's isomorphic in a trivial way because right because if the tangent space is space of all vectors tangent to n, well, that's the same. So there's a natural isomorphism between the two, and so we can sort of make a pun and say that they're the same. And so that just means that we have a map from R2 to R2, or at least a two-dimensional vector space to itself. And more than that, we can even show that it's self-adjoint, so it's a symmetric matrix in a sense. And so the symmetric part is going to be very useful later. Okay, so that's for the Gauss map. We'll come back to it later. Because we're in Euclidean space, we have like a natural affine connection, nabla, which we simply obtain by inheriting the one from Euclidean space. So because the Euclidean space is also a manifold, but with a trivial connection, we can get a connection on our surface S simply by like restricting. So notice that here is simply the identity, or yeah, the identity. And to get the connection on our surface from that one, we simply project on the tangent space. So we say that the covariant derivative of x, so vector field x along vector field y, is going to be the projection on the tangent space at P of S of the derivative, so it's here simply the directional derivative of vector field x alongside vector field y. And so because we know we have the normal vector, we can express it as this. Okay, so far so good. Let's try and compute the torsion and curvature for this. So the torsion is actually very easy. It's the projection of this thing here um, by definition of this D connection here, right? It's the identity, so we're just taking the normal derivative. And because we assume that our surface is nice enough, well, we're taking the derivative with vector 2, and if it's nice enough, these commute. So this is equal to 0, and so projecting 0 onto a tangent space still gives a 0, so the torsion is 0, so there's no torsion. You might recall that there is in fact a unique, maybe not quite unique, but like a nice connection to use typically is the Levi-Civita connection, which is compatible with the metric and torsion free. Well, usually you can get the Levi-Civita metric simply by doing this process of embedding your manifold in some Euclidean space, inheriting the metric and inheriting the connection, and it works. So torsion is 0, so we don't care about it. The curvature, it's a bit more involved. So these three dots here, they do a lot of legwork here. But if you crank the crank the wheel enough, you eventually end up as something like this. So the the curvature with respect to these two basis vectors on some vector field W, I can simply express it as in the two vectors, so dn times theta and dn times d sigma. And more generally, if I forget about these basis vectors, for any u and v, I still have the same. So W, so inner product of W with the differential map and apply to U, and so on. That's we get this. Um, if we take one more inner product, so again, if this is not clear, either wait for it to go to be over or read the book. It's a bit clearer, but not too much. If we take the inner product of this with another vector field, we get this expression, and okay, we had like AD minus C BC, so this sort of looks like a determinant, and so let's write it as one. So we can write this as the determinant of a 2 by 2 matrix as this. And if we do a couple more manipulations, we can sort of extract this differential, right? Because dn here, you can think of it as a 2 by 2 matrix. And so we would like to isolate it, and it turns out we can. And so if we extract it, we eventually get the determinant of n. Actually, it should be the determinant of dn, I think. Oop, dn times determinant of this matrix. And so we'll define the determinant of dn, right? The determinant of a matrix. We'll call that the Gaussian curvature of my surface. Okay, so onto I have one example and then a bit more explanation about this Gaussian curvature. But note that we've managed to link this Riemann curvature, but that's a bit hard to understand, to something a bit clearer. It's just a scalar function that you might already guess is a bit of the similar to the curvature of curves that we saw before. So let's give an example. So very simply, let's take the sphere, unit sphere. So all the points, not unit sphere, but all the points at distance r from the origin. Um, it's very easy to see that the normal vector here is simply p divided by r, right? Because I want to normalize it. And so you don't need to care too much about this, but essentially the curvature is going to be 1 over r squared. And okay, you might think, why not 1 over r, right? Because for curves it was 1 over k, but we're in 2 dimensions, so maybe we need to take another power. So at least the curvature for one sphere is a constant 1 over squared, 1 over r squared, sorry. Okay, so slightly more complicated example. Second degree surface, but parameterized by this. So z here it's nice because we're sort of making that z is equal to this. And so if we do again the calculations for this, we find that the curvature is given by 4ab times this expression on the bottom that's always positive. And so depending on a and b, we can have sort of three cases. Either k is smaller than 0, so one of a or b is negative and the other is positive. and that would correspond to something called a hyperbola. So we would have one direction like this and one direction in the other, and so that's you can call that a saddle point. Um, you might remember that saddle points are usually something that make you sad when you're trying to optimize neural networks. Um, and indeed, that's because they have negative curvature, so you can have some nasty stuff happening. Um, Another thing that can happen is if k is equal to 0, so let's say one is equal to 0 and the other is negative or positive, it doesn't matter, then we have essentially a cylinder because we have one direction where essentially it's a flat, so in this direction it's a straight line, but then the other it's essentially a circle or a positive curve. And then if k can also be positive, and then it's more elliptic because it's essentially a sphere or something close to a sphere. And so these are the three cases, and they sort of like describe these three types of, of quadratic curves. Okay, so I do have like a better intuition about what this curvature and why it's a determinant. So you might remember I defined the curvature as determinant of Dn, which is a matrix, a 2 by 2 matrix. And we also know that Dn, well, it's a symmetric matrix, and so that means it has real eigenvalues, so that's nice. We also know that the determinant is simply the product with the eigenvalues, and it also has, because it's symmetric, orthogonal eigenvectors. And so the curvature is the product of these two eigenvalues, kappa 1 and kappa 2, and we can find the orthogonal eigenvectors, let's say u1 and u2, and they're going to be like the direction where the curve bends the most and bends the least. And so this is something you can do to like bring back the old what we saw about curves, is that okay, I have a surface. Maybe it's a bit complicated, but I can always like take a slice. Let's say I take a slice of my surface along a plane that gives me a curve. And it's a curve in 3D, so I can apply the curvature and compute the curvature I had before. Now, what happens is that I can I can rotate this plane whichever way I want, and I would get a different curvature. But these like vectors u1 and u2, they're like directions at that point. They're the ones that are going to be the largest and the smallest curvature. And so in a sense, it's like they're the most interesting directions to look for the curvature. And okay, that's all I had for today, or at least in terms of explanation. So, and also we're good for time. So yeah, thanks everyone.